No place to hang out or washing, and then I can't blame all on the sun. Oh no, we're gonna rock down to Electric Avenue, and then we'll take it higher. Oh, we're gonna rock down to Electric Avenue.
Today we're looking at electric current. Being able to control the flow of charge has revolutionized our lives, from lighting our cities, to powering our factories, to driving the information revolution with computer chips and semiconductors. Understanding electric current is fundamental to modern life. So let's dive in. First, we're going to use the water analogy to help us understand circuits. Water analogy is very helpful. So just like being able to control the flow of water led to advances in civilization with sanitation, can apply that to electricity. So the first thing is, usually for a system of water, you need a source and you have to have a pump to get everything going, like a dam, water tower, etc. So when we're looking at electric current and circuits, we're going to start off usually with some kind of battery or power source. Whether we plug into the wall, which is usually what we call AC power, or we use, everyday batteries, AA, AAA, D-cell batteries. That's DC, direct current. Next, we control the flow of water with pipes in your home. So for electrical circuits, we're going to use wire, usually made out of copper. Next, flow of water current inside pipes. We can think of the flow of positive charges inside an electric field that's set up in that wire. And what's kind of goofy, we'll talk about this in a second, is technically it's electrons that move, but positive charges is what was first called conventional current that Benjamin Franklin actually defined. And that's what's stuck. So everything's always defined from a positive reference frame. And then finally, you can slow down the flow of water by sticking gravel or pebbles inside a pipe. Or if it's a faucet, you would close the valve there. So in electricity, we think of that as the resistance of the material. And it's a measure of how tightly bound those electrons and charges are to that material. And some materials have a very high resistivity, and we use that to our advantage. Next, let's dive right in and define the definition of a voltage source, which is our battery. What's the purpose of a battery? A battery is simply an electrical device that delivers energy to charges. And really what a battery does is it sets up an electric field that provides energy to move those charges through. And these are some pictures of early batteries that were developed. And a common misconception is that a battery provides electricity. But that's actually not true. The electrons and charges are already inside the wires, a light bulb's filament, your cell phone circuits. So really, you don't get any charges from a battery. What you get is energy. And so usually you have two dissimilar metals called the electrodes, and one of them likes to give away electrons, one likes to grab them, and that's called technically an anode and cathode for the positive and negative electrode. And you can actually make batteries out of zinc, nails, copper pennies, and then usually you need what's called an electrolyte, a weak acid, to get the chemical reaction to go. So like lemon juice is a classic homemade battery with a little science experiment you might have done when you were in elementary school. Next, we got a quick recap of the definition of electric potential, more commonly called voltage. Electric potential has a very specific definition, but it's a little bit abstract. It's potential energy per charge. So we like to use the analogy of height against like gravity, so like the height of an electric hill, or we can think of pressure, like water pressure. So in this case, electric pressure. Electric potential is defined as V equals PE divided by Q. So in other words, 1 volt of electric potential is when we give 1 coulomb of charge in an electric field 1 joule of potential energy. So in a water system, there's a pump. You would pump water up to the top, or in most towns, you got a water tower. So why are water towers, shaped so funny? Well, the idea is you want to put water at a higher potential so that as the water tower drains, even if it's 90% empty, you still have water above your head to flow from higher to lower pressure. So here's an example of voltage in a real-life circuit, which you're going to do in lab actually. So usually, build a circuit. This is just a diagram of what one will look like. You start off with battery. In this case, we have 2 batteries, like 2 D-cell batteries, and then we got 2 light bulbs here. And then the charges flow through and the light bulbs light up. And it's exciting. So anyhow, let's say we have 2 D-cell batteries. So technically that would be 3 volts if they're brand new, because each battery is 1.5 volts. What that means is we're giving 3 joules of energy to every coulomb of charge that flows through this circuit. And technically, we have current flowing. In this case, it's going to be in the counterclockwise direction. Current is a flow of positive charges, and this longer line is a positive terminal of the battery. And then let's say it hits this first light bulb here, and the voltage difference across this light bulb is 1 volt. So an analogy would be like you went up a sled hill, and it's 3 stories tall, and then this first part of the hill that drops is 1 story. It's a 10-foot drop, something like that. So 1 volt of potential difference means that 1 joule of energy is changed into heat and light by the light bulb for every coulomb of charge that flows through that light bulb. So let's take a look at what's going to happen now for this second light bulb. If we used up 1 volt across this first light bulb, then across this second light bulb, we must use up 2 volts of electric potential. And what that means is 2 joules of energy will be converted into heat and light for each coulomb of charge that flows through this bulb in order for the circuit to conserve energy, because we had 3 joules to start with. So the analogy would be, as we go down the sled hill, if we were up 3 stories at the top of the hill, as we come around the hill, we drop 1 story, we're going to drop 2 stories across that last hill. That would be our light bulb, would be the analogy here, to get us back to the bottom. And then we'd have to run up the hill again or take a ski lift, which in our analogy would be the battery.